Today is some kind of educational seminar. I have to speak English because we have guests. I'll talk about virtual machines, containers and solutions, how to run your code for another platform, for another operating system, for another hardware on your PC, or how to mix all these things together. So let's start from this. So several topics here. So the first one, some basics about operating systems and hardware, how the modern operating systems run applications, how drivers works with the kernel, how user space works with the kernel, then ideas how to virtualize equipment and build virtual machines, then ideas about lightweight containers like Docker, and several things about hardware and how to mix all this stuff together. The first and the important thing about the modern CPUs. So in ancient time, when you worked, for example, with DOS operating system, memory model was flat. You just have a memory, you just have something that is named BIOS and kernel, but it's not protected, and all pieces of software had the same privileges and can do anything you want. After that, Intel and most of producers of CPUs for even microcontrollers, they introduce idea of hardware protection. Then CPU has several modes of execution of instructions, and the most restricted one is a mode for application. In this mode, you can't manage hardware, you can change paging, memory, organization, and so on, so on. You can just use the things that you have. And on low level, in kernel mode, in different protection rings, you can get more access to hardware ports, to memory, paging, to some internal stuff inside of processors that control the system behavior. So things that we need to know. So there is a high priority, the most important part is the kernel. Kernel does anything it wants. Then on the higher level, amount of privileges that you get becomes smaller, and if you try to run something that is prohibited, kernel gets an exception. So it's the same as a division by zero, you get an exception, and the same like that. That's it. The next part about operating system and architecture in high level. So, yes.
May I ask a question?
Yes.
How many rings are used in practice by operating system?
Windows uses 2, 0 and 3. The ring number 0 and ring number 3. Other two are not used. I'm not sure about Linux.
Are there any difference between ring 1 and 0?
No. I'm not ready to answer the question.
No difference as far as I know.
Maybe it's possible.
So in practice, we can use 4, but in general, nobody uses first and second ring, just 0 and 4, 0 and 3.
Okay, actually, this level of details is not important for us right now. Another important thing that, just a reminder for you, is that Linux and most of modern operating systems for desktop computers have two pieces of software: the kernel itself that manage hardware, and user space software libraries, applications. It's what we usually do. And drivers and all the stuff, they are below this red line. It's in the kernel. So what is important here is that kernel has own address space and works with own pieces of memory that are protected from user, but it's the same memory address space for all drivers, for all applications that are executed on top of this kernel. And kernel stores some kind of context information about each program, each process. And process is not something that is executable. It's just a set of objects, flags, and state of the program. it's not that you can run. And each process has its own virtual address space. Something that is related to this application, like mutex, some file descriptors and so on, that is managed by kernel. Mutex case, it's for Windows, for example. In Linux, mutexes usually are user space mutex, so they are not kernel space object. So we know from Linus Torvalds that, let's say, he guarantees that on this level, on this red line, the API is fixed, so they don't break API, besides cases when it's really needed in terms of security. So there are gray areas when it's possible to make something harmful, and Linux developers time to time try to fix these gaps, but the main goal is to have stable API between kernel and user space. And the last item related to general things about operating system is about the pipeline, the way how the things are called from kernel. So there is some kind of API, and API works the following. There is, for example, an interruption, and if you want to call something from the kernel, user space application just raises this interruption, and there is some kind of API that you should put your parameters into registers or into stack in some particular way. Then kernel knows how to extract them, handle this, and return back the result. For example, if you call printf function or try to output something to console, it raises system call. System call switches the processor from user mode to kernel mode to ring 0. This is handled, and we get back to the application. Again, this red line, it's a border between user space and kernel space. Modern Intel processors, they contain special instructions like leave, enter and leave to switch between modes. It's not just interruption, but the overall idea is the same for ARM, for MIPS, for Power, all architectures. It's implemented in the common way everywhere. So, what about virtual machines and idea to emulate computer system with another computer system? So you can do it in two ways, on two different levels. So you can emulate full hardware stack, full hardware platform, and run your target operating system in the same way as it is done on hardware. And other idea is to not to emulate full computing system, but emulate some piece about CPU instructions and memory scheme, and do it on process level. How can it it can be done in different ways, with different hardware support, with different level of quality and accuracy in terms of hardware emulation. And the first thing that you have to do is to support target instruction set with a lot of small details and memory model. Then if you want to emulate everything, then you have to emulate disk, port some hardware like a video or networking or any kind of I/O pieces that is designed to be there for real hardware. Then there is very, very strong implication about performance, because if you want to run things once and get the result, it's okay. But if you want to use it regularly, performance is very important. So as I said, there are several ways how to achieve this kind of virtualization. The first and the most obvious one is just to interpret instructions of the program that you have. The oldest maybe solution for Linux that I know is the Watches program. It's an interpreter for x86 instructions, and it emulates not just it can not just run program instruction by instruction, but it contains a solution for emulation of some subset of hardware like disks, video, and so on. And it even includes BIOS implementation. So the program that is run under this simulator, this virtual machine, it runs like on a real hardware. Even BIOS interruptions, they are supported as designed. So you can run full stack operating system. For example, the last thing that I saw about this simulator was a Windows 95 or 98. I haven't tried it for a long time, and it worked. So the most important thing here is the performance. It's not a real, so you have very serious performance drop. Another alternative, if we speak about not operating system in general, but about single process, for example, you want to run program for ARM on your PC or vice versa, there is a solution with the QEMU. QEMU allows to, I'm not sure if it's pure interpreter or JIT, but it allows to run programs for Linux for non-native CPU. For example, you can run ARM v7 or ARM v8 program on your PC with this program, and it runs in the following way. So ARM, this QEMU has a binary that is registered as a runner for ELF programs for particular target, for example, for ARM. And when you start the program that is built for ARM, a kernel invokes this runner, this helper, and it does all things for us. So, for example, you can bring your favorite program from Raspberry Pi and run it on desktop, and it will work in case if you bring all libraries, runtime libraries with you. Alternative solution is try to run not for another hardware, but run program for the same hardware and for this, with the same instruction set, but with another operating system. And here, hardware, this task is simpler because you don't need to interpret instructions, all instructions, but you just need to ensure that you can serve all critical instructions that manage hardware, things from this ring 0. So things that operating system does, you should emulate these instructions. All other regular instructions like mathematics, it can be run on CPU natively. What most of hypervisors does for you, and modern CPUs, Intel CPUs and AMD CPUs, they contain set of instructions and set of modes how to do it in the most efficient way. So modern Intel CPU can even handle paging for virtual machines in the same way as it does for native system, and it reduces overhead because otherwise every time when you try to do paging in virtual machine, you can handle it on software level, and it's not efficient. And the last idea and thing that is actually used in most cases right now is a para-virtualization. So the idea is that let's throw away this step to emulate paging or emulate video I/O. Let's hack the system that we want to run inside of our virtual machine, replace calls to hardware with some calls with a special protocol, and hypervisor knows how to deal with it, and it can do this with instructions of native host. For example, Windows and Hyper-V, hypervisor does it, and it was implemented a lot of time before. So if you run Windows inside a virtual machine with the hypervisor, so it renders graphics and some pieces of it does some pieces of the work with the native, with the host system. So there is no special driver, there is no pieces of some rendering pieces inside of virtual machine. These steps are delegated to the host system, and host system does it for you in a more efficient way.
I have a question. Is it possible from guest operating system from ring 0 access to ring 0 memory on host?
I think no. It shouldn't be. It's part of solutions from Intel and AMD for hardware virtualization support. So they isolate pages and they implement paging on hardware level. So modern CPUs, it's one of options. It's not the only thing that they do, but one of options. Modern Intel CPU can handle several paging systems, one for the host system and one for each of virtual machines.
And who will handle such wrong construction? Host operating system?
Yes. It should return somehow to host kernel. Okay. So these ideas about virtualization are very heavy because you need to emulate some pieces of hardware. You have to work with some special instructions and handle them in a particular way. In worst case, you have a lot of interruptions because the kernel inside of simulated system, it tries to trigger this and this and this events in hardware, and you have let's say exceptions, some traps every time, and it's very expensive. And so actually virtual machines and previous step, they triggered kind of boom of clouds and virtual environments. But again, it's not the best in terms of performance, because every time when you want to make this virtualization, you pay for all these activities. Alternative way to do things is not to try to virtualize kernel, or not to substitute some implementations of BIOS, disks, networking, and so on, but re-implement host system kernel in the way that it can work with that can isolate applications in user space and provide for each application in your user space different set of things. For example, provide different root file system and provide different capabilities in terms of networking, hardware access, and so on. So it's kind of another layer of access management in kernel. And your application just runs in a regular way. It's just a usual Linux process. It's what actually this OS virtualization provides as an idea, and it's how the things are implemented in Linux. So modern Linux kernel allow to manage not just permissions of applications, mean you can write to the file system, or you can't open this device because you don't have permissions. Kernel can manage API calls by groups. So for example, you can open file, you can write to file, but you can't mount file system, or you can't get access to this particular hardware. It's not a permission on file system level, it's a set of permissions on API calls level. And kernel is able to run processes with different environments, with different root file systems, with a different set of users, groups, and all this stuff. So it looks like you have one Linux kernel and several Linux distributions on top of it. And all of them are independent. They talk to the single kernel, and the single kernel handles hardware for you. It shares permissions, it manages permissions, it manages resources. It works in the same way as it should be. So we don't have overhead to synthesize some hardware, or we don't have overhead for extra kernel operations, everything in our native kernel. So if we speak about Linux, there are two public branches, two popular branches. There is a LXC set of instruments, and there is Docker. So both of them are kind of set of tools and utilities on top of options that are available in kernel itself. So any questions about it? Okay, so let's go ahead to practical part of things. So the first one, what concepts Docker proposes to us, and what should we understand? So the first step, if you want to run several independent environments and that are named containers at the end, you need to describe how this environment looks like, what kind of file system, what kind of files are there. And Docker proposes a Docker file format. It's something like shell file. I'll show you later. Then when you have some kind of formal description of environment, you can build it and get some binary, let's say binary file, some binary representation of what you want. And this binary representation, it's portable. You can take it from your host and move to another system. Then, as soon as you have several environments on your host and they are isolated, you need to talk to them somehow. And one of the things that Docker proposes is it's a kind of options in kernel again, but it's things for convenience. Docker generates for you virtual network interfaces, and containers looks like a virtual hosts that are connected to the same network or to different networks, and they are connected to the host with network address translation. So in terms of network topology, it's just a set of hosts that are connected to each other in some way. And you talk to these isolated environments over network. Then usually you want to put some data to this isolated environment, and Docker provides a way to mount pieces of your local file system inside of this Docker container. It works like a regular Unix mount, but for this is isolated containers. Several words about the file system and how Docker organizes these containers inside of it. So this system is designed to reuse pieces of this isolated environments as much as possible, and we can divide our isolated environment on two major pieces. So if you run any application, then you have some baseline operating system libraries, data files, and so on that you don't want to change. It's some basic stuff. And you have some data that is generated by the process running inside of the container. It's something that you need right now. And these two parts are decoupled. Docker introduces Docker image concept. It's some fixed data that can be changed by the process inside of the container. And Docker container, it's a additional thing on top of your file system that you define here, that is generated by a process that is running inside of a container. And to do it, Docker uses a layered file system. So it doesn't just write files to the disk, but it stores deltas. And looking here, in most cases you have some basic operating system, then some packages on top of it. For another application, you have the same basic operating system plus packages on top of it. Basic operating system, it doesn't mean kernel. It means libc, some basic runtime libraries, the same for distribution. And this fixed part, it's layered too. So Docker stores your binary image as set of deltas, and in runtime, when the container is started, it compiles all things together and run this way. So it works in runtime in the following. When you start the process inside of container, you generate new container. They inherited from the same basic part, but runtime data is different for each instance. Couple of words about Dockerfile and how to do it. So Dockerfile is a plain text file, and it consists of some keywords of a Docker and then just lines of shell commands. So from its original point, what you want to use as a base image, you can start from scratch, and your environment is empty, nothing there. If we start from Ubuntu, as here, it downloads the base Ubuntu image for Docker from official site, and we use from these binaries. Then we can define user, switch to this user, I mean not to create, but switch to this user, make some commands, and its environment, run, it's just run the command. And then the last one, CMD, it's an entry point, what should be done inside of this environment. And we have two steps. So first of all, we should build this environment, and to get image, it's done with a Docker build. Then we can run Docker run command, and it takes this base fixed constant environment, runs this entry point as a process, and it generates yet another layer with the current data that is generated by this process, and so on. What is important here is that every time when we call Docker run, it doesn't introduce new kernel, new virtual environment, virtual machine. It generates new Linux process with a set of access options. This process can access to this and this API, and that's it. And one of options here is a root file system that is used by this process, and this Docker image, it's a file system for this particular process. So it's not enough usually if you just want to build some environment and run it. In many cases, you want to move it, distribute it somehow, to bring it to another host, and there are facilities to do it. So there is a project that's named Docker Registry. It's a storage for binary images that are built. So it stores layers, these layers that I described, with the pointers, which layer, so with information for each image, which layers are used. So it works like a Git. It's very close to Git. Each layer has its ID. ID is some kind of hash sum of this layer. Then you have a tags. You can pull and push these images, and this pull and push works with your machine and remote host that works as a Docker registry. Docker, as a team, as a company, they provide hub Docker.com. Docker Hub is a storage, public storage for Docker images, and a lot of companies publish their Docker images there, public official Docker images there, and it's storage by default. But you can pay money for them, and you'll get closed instance of Docker Docker registry on their site, or you can set up Harbor. It's yet another Docker registry that you can install on your hardware on premise. You can use Docker registry in GitLab. It's in one of pieces in GitLab, and so on. So as soon as you have an opportunity to run process in a isolated environment, and you can move these environments, and you can run any amount of environments you want, then it's reasonable to manage them like a cluster. So what you can do, you can deploy several hosts, physical hosts. You have n physical hosts. Then you have m containers and tasks that you want to run in this isolated environment. And one of the things that you need to do usually with these containers is to organize them somehow, balance, manage access, and so on. And one of modern tools that I use for this is Kubernetes. So it's a solution to run containers, a lot of containers on any scale, actually, in any amount of hardware. So Google pushes this solution. It's the, how to say, it's a common way to do it right now. Then Docker is a good solution for continuous integration as an environment for continuous integration testing. And you can run, yeah.
Can Kubernetes manage resources? I mean that if I want to run one Docker container per one CPU.
Yes. Okay. So if you want to run something inside of container, inside of this isolated environment, you can do it with all modern continuous integration solutions. And vice versa, you can use Jenkins, GitLab CI, and all these tools to build these Docker images and manage them on the go. So, and there is, for example, good linter to find problems with the Docker files and so on. So this ecosystem is growing continuously. So why do we need Docker? So Docker is a good solution as if you want to provide distribution package. If you want to give a tool, or if you want to give a, for example, web service to somebody, and not to worry about host configuration and environment. You just push it to Docker registry, then pull from Docker registry, and start the container. And you always know everything about libraries that you use, about options, about environment, about file location, everything. So it's a portable application that you can run. Then, again, it's a good solution for continuous integration and testing. The same idea, you can reproduce any environment anytime you want, in any scale, on any host you want, multiple times, and you don't need to go to the host every time when you want to update something. You just change your Docker image, push it to registry, and pull it from all hosts you want. That's it. Docker is a good idea to use for cases when you need some kind of clean room. So some environment that you can restart from every time from scratch and make experiments. Or, for example, I had a task, for example, to check that Debian packages that I generate for the project, they can be installed to the system. And what is more important, we had a task to replace standard OpenCV distribution inside of Ubuntu with our own packages. I can do it with my host system. I can remove host OpenCV, install things on top of OpenCV. But every time when I do this, I introduce some states, I change my file system. I can't roll back to the original state. It's pretty hard. But Docker, it's a thing that you can start every time from the same state, and you are 100% sure. And the last thing, technically, you can run any kind of Linux distribution on top of your Linux distribution. It means that you can test your application with Ubuntu 14.04, 16.04, with CentOS, and so on. The only restriction here is that your host system, kernel in your host system, should be capable to run system calls to this kernel from this isolated environment. So if you run testing, you don't need to run 10 distributions, have 10 hosts, or have multi-boot system with 10 versions of Linux. You can run 10 containers, run, stop, and so on. Then, as soon as we run on real hardware, we don't want to simulate hardware behavior, there is a good idea to try to attach some hardware accelerators to the program inside of container. And it's what we often need for continuous integration in computer vision. For example, you have GPU, you have some accelerators, and if you want to run application in this isolated environment, then you should need a way to attach hardware to this container. And several ideas, several implications about hardware, how it works. and how to do it with Docker. So in general, every driver, every hardware piece that we have in Unix system, it provides some device in dev folder, and all interactions between user runtime and this device, they are just open, read, write, close, plus several IOSTL calls. It's a key value request to the device, to the driver and to device. And high-level runtime APIs like CUDA, like OpenCL, OpenGL, and so on, they just kind of sugar software wrappers on top of these calls to talk to driver. The same actually for USB stack. So USB provides some basic level, kernel provides basic level support for USB. And for each device that you connect to your PC, you have dev something in file system. And you have libUSB library on top of it for let's say non-standard USB devices. If you work with storage, then kernels work for you because it's well-known type of USB device. But for most other types of devices, software is implemented on top of libUSB, and again, it's a read-write octal call for some device, save the file in dev file system. So the last one, there is udev. It's a daemon and plus some pieces in kernel that allows to handle runtime events like hot plug devices that you connect flash card or disconnect flash card. It's a side thing. It's not so important here. So technically, it means that everything that you have in your system that is available for your kernel is accessible for the container. The basic stuff is implemented inside of Docker. For example, Docker mounts proc CPU info and assign files from proc file system inside of container, and container knows on which type of CPU you run, and it makes possible to detect CPU architecture features like AVX or Neon and go ahead. Then Docker provides options to like CPUs and memory to limit amount of resources that you provide to container. So actually Kubernetes uses this option to do the thing that Alexei asked before. So you can say that this container consumes only single CPU and this amount of memory, and kernel controls these options. It's a little bit tricky, but we can treat that we can limit amount of CPU and amount of memory that is available for this container. Then
and Kubernetes manage it.
Yeah, it uses this option of Docker to manage resources. Then you can mount, let's say, mount any device that you have in a system inside of container. So it means that Docker allows to put your dev something device inside of container, and you will see dev something device inside of container, and all programs that know how to deal with it, they can work with this device. In case if you don't know about details, there is a privileged mode. This mode of Docker container that unblock access to all APIs and all hardware pieces that you have in a system. It's kind of dangerous way because it's unsecure in many places, and it brings all hardware blocks that you have in your system inside of container, so you can do what you want. And piece of sugar here for guys who like NVIDIA. So NVIDIA provides Docker, NVIDIA Docker runtime. It's a piece, it's some kind of convenience thing to run CUDA programs with Docker images and not worry about low-level details. But technically, all things that NVIDIA Docker does for you, it can be done with other options. It's not mandatory. Couple of details and tips how to deal with devices. So there are a lot of cases when software is developed with the one device in mind. But it's not true for continuous integration. For example, you have a lot of mobile phones and you want to test for all of them. Android is the good. He knows how to manage several devices connected to the host, but let's imagine that it cannot do it. In hardware, let's say, in ancient world, you have to buy one PC for each phone, run independent build and test on each PC. So you spend a lot of money and spend a lot of electricity and resources to do it. With Docker, you can do the following. You can attach single phone to one container, and software stack inside of this container sees just one device and can work with it. So you can have hundreds of devices connected to the same PC, split them between containers, and everything works as you design. And USB helps us because USB protocol has a serial number, and a lot of devices, they have unique serial number, so you can connect a lot of boards. Even JTAG adapters from Linux, they have own serial number each device, and you can work, for example, with several boards together, manage several boards and work with them with a single host. So, what else? So there are several interesting side effects about this split. So first of all, to use Docker with hardware, you should know about the driver and how it expects to work. For example, drivers for CUDA and OpenGL often know that the GPU can be utilized by several processes, and driver is ready to be opened several times, and it can manage several applications together. Other devices like JTAG adapter, they are not ready to be used by two applications in the same time. With Docker, you can do it. It's achievable configuration, but it breaks the hardware behavior. So you should be accurate with this. Then we have hot plug devices like USB drives. Then there is UDEV. It's a daemon on your host system that manages access and some events. And you should know about it. And important implication that by default, even with the privileged mode, container doesn't get notifications about USB devices and hardware configuration changes that are triggered by UDEV. Then there are local bugs and some features that prevent to use hardware with containers, and you have to hack something, but it's a rare case for now. So actually, as I said, it's purely software feature. So if you want to run such kind of isolated environments, you don't need x86 system in particular. Technically, you can do it on any platform with Linux, with a modern Linux kernel. You just need to have this layered file system support and some options related to C groups and namespaces enabled in the kernel. So technically, you can run all this stuff on Raspberry Pi with ARM chip, and it works. Even Docker guys and the guys from Raspberry Pi, they have official relationship, and Docker supports Raspberry Pi as a target. The only implication here that so we run the code inside of container natively on the system. It's just another process. It means that the content of the container should be capable to run on your physical hardware. So you can have Ubuntu 18.04 for x86. You can have Ubuntu 04 for 80.04 for ARM, and any kind of platform like that, but they are different Ubuntu images. There is important implication that all this stuff, it's most for free in terms of performance, because at the end it's just a Linux process. But all these extra things like virtual network adapters, like layered file system, it takes some memory. And in cases of very small boards, it's not, it's not handy. You just eat extra RAM. And if it's important for you, it's kind of overhead. then actually it works not only on Linux, it looks like, at least. So Docker provides distributions for Mac, for Windows, and it works in a different way. So for Linux, there is no, for Mac, there is no capability to run native Linux applications on top of it, no C groups and all other stuff. And Docker just make a trick. It runs small virtual machine with Linux kernel and then run all containers on top of it. So it's seamless for you. You can just pull container and run it, but at the end, it's a virtual machine. The same for Windows, besides one point. So a couple of years ago, Microsoft and Docker, they implement native containers with Windows. And it's approximately the same as we have on Linux, but with Microsoft options, with the smell of Microsoft, let's say in this way. And for hackers and for guys with the crazy ideas, technically you can run Android inside of container, because Android it's based on top of Linux. There is only thing that you should know, that Android uses custom Linux kernel with extra modules and options, and these APIs should be in your host kernel. So if you rebuild your host kernel with binder support and some other extra features, technically you can run piece of Android user space code inside of Docker image, and it will be kind of for free for you. And I know about successful experiments of this type. What about Windows? Well, let's step back. There are 3 modes of Docker and Windows that you can use. So the first one is about virtual machine, and the same as a Mac. We have small virtual machine with Linux, and all containers are executed on top of it. The next item is to run containers in virtual machine, native Windows container with a virtual machine with Windows inside. So it looks like a container, it behaves like a container, but it's done on top of virtualization. And the third option, the most interesting actually option, is to run containers as isolated processes in with the same approach that is done on Linux. It should be kind of for free. I mean in terms of performance, it's again just a process on Windows, but it's not so simple to do it as it's done on Linux and Unix-like systems. And it leads to several interesting things. So the first one, these containers with the native Windows, they are built on top of Microsoft Server. And it means that you have Microsoft Server, you have to pay for license or something like that. You can just distribute it, again, because it's Windows. There's no UI, no GUI. You can't get this message about access violation, blah, blah, blah. It goes somewhere and you don't see it. It's very important to know if you want to start to work with it. There is no package manager. You can just install your favorite apps with apt-get install. Every time you want to install application inside of this container without UI, it's kind of blind installation. There are ways how to do it for different programs. It's done in different way, but there's no general way to do it. Then, even if the size of base Docker image is several gigabytes, it doesn't provide full Windows APIs. For example, there is no multimedia stack there, not video for Windows, not media foundation. And if you just build OpenCV on your Linux host, you can push this OpenCV there, but you can't run it because there are no some libraries, DLL libraries, so it doesn't start at all. So if you want to run, for example, with OpenCV, you have to build OpenCV without Windows, without multimedia stack, without some pieces that are usually there on regular Windows system. And there's no hardware support for now because it's more tricky than just mount some dev blah blah blah. And Microsoft and NVIDIA, stepping back to NVIDIA Docker, they don't provide support for CUDA, OpenCL, OpenGL, and I don't know about the plans when it can be done and if it's possible at all. So that's all. It will be great to have some kind of practical session to show how it works on real hosts and how to do it, but it will be later. So do you have questions?
Later mean next time?
Next time, yes. Not today. Okay, 5 minutes for questions.
Okay, so what is the most common way to communicate between containers? Is something like HTTP protocol or it is more low level?
Actually,
it depends on.
It's up to you actually. So what Docker provides to you, it creates virtual interfaces and it assigns API addresses for them, and then you can build network on top of it. For example, you can run this and this and this containers in one network, this and this in another network, and containers that are in the same network, they can talk to each other. For example, you can run a database plus web server plus something else like monitoring inside of this group of containers and expose port of one of the container outside. It's mapped to the port of local system. And for example, if you have a database, then you have a network port for this. You have web server that has network port, and you have something that has open network port. So you can hide all of them besides one that is public port for external access. And all this stuff is managed by IP tables and networking system inside of Linux kernel. It's not yet another thing. It's a part of Linux kernel already.
And what is the license for Docker?
Good question. I need to check. So it's let's say free enough, so you can. So the Docker itself, it's kind of umbrella on top of features in Linux kernel. So technically, you can reproduce the same without Docker, but it's not so convenient. You have to do a lot of things manually. The Docker as a tool, it has very permissive license and it's very widely used. But every time when you work with Docker image, then you should speak about the license for content outside of Docker image and legal applications. Because, for example, if you create a distribution on top of Ubuntu and put it and push it outside of your team, give it somewhere to somebody, it means that you distribute piece of Ubuntu plus your code, and it's some kind of legal implication for large companies because they are afraid to distribute pieces of Linux, for example, because of GPL, LGPL, and so on.
So, but Docker is not open source project?
It's open source project. So the major part of Docker and things that I described, they are open source. You can contribute to their project if you want. So there is a company that is named Docker, and they create this project and this product, and they support it.
And how do they earn money?
They still do not, actually. So they get investments from a lot of companies, but they still can't find a stable way to monetize their work. So it's still, so they have a commercial support that you can get some extra features, but as I know, they are not profitable company still. Yeah.
In case if we have some proxy settings on the virtual machine, can we put them in the Docker file, like with the daemon?
Proxy settings. So it's not a question about Docker. It's a question about IP tables and network topology. So, for example, if you have proxy settings that is set as global environment, I mean environment variables, then you can put them as environment variables, and network packages will go through network translation procedure as a regular host. So it's the same as you have an AT server plus several hosts in this network. So it's the same, nothing special there. So that's it.
Thank you.